Next major topic is the subspace topology. This one is another one that's pretty weird the first time you see it, but with enough practice, you get used to it. The idea is that if you start with a topological space, which we're going to call X, the open sets of which we're going to call tau, and you take some subset of X, call it Y, then you can define a new topology on Y. And doing so, you'll say you give it the subspace topology. So this set tau prime right here that I've defined is what's called the subspace topology on Y. And so you say that, oops. You say that Y is a subspace of X using this topology. The topology is really, it's in one-to-one correspondence with the open sets of tau, the open sets of X. But what you do is you take each of those open sets and intersect them with your subspace. You intersect them with Y. Why does this make it a topology? Well, you can sit down and verify that if you want. Why is it useful? I'll show you some examples. First, let's note some other definitions. Misspelled subspace. The subsets in tau prime, so I'll call them U prime, because why not? But keep in mind U prime are just the things I'm calling U intersect Y, where U is in tau. So U is some open set in X, U prime is that open set intersected with our subspace. Those subsets are called relatively open in Y. Relatively because they're open relative to your subspace. Similarly, if you take some closed subset of your larger space X and intersect it with Y, then you get what's called a relatively closed set in Y. Okay, so quite a few definitions, but they're all related to the same thing. They all come back to just remembering what tau prime is, the subspace topology. Okay, so let's see some examples where this can be used. One, let's think about the real number line with the usual topology, meaning Euclidean. And let's think about this purple subspace that I've drawn. So the interval from 0 to 2 closed on the left-hand side, open on the right-hand side. So we're going to think of that as a subspace, meaning we're going to actually imbue it with the subspace topology. And we're going to think about some subsets in particular and see if they're relatively open or closed in this purple subspace Y. All right, so first thing we want to look at is the set A, which I've defined as the interval from 0 to 1, closed on one half, open on the other. Where is that going to sit? Well, that's going to be right here. It's A. Note it's certainly not open in X. It's not open in the real number line because, hey, it's closed on one side, right? However, it is relatively open in Y. Why is that? Well, you can see that it's actually the intersection of some open set in X, call it U, intersected with Y. Right, so if I take that teal set U and intersect it with Y, so A, sorry, I switched to red. A is the intersection between U and purple. Right, A is the intersection between those things. U is open in X, Y is our subspace. That's the definition of being relatively open, right? It's A is equal to some open set intersected our subspace. Okay, similarly, How about I look at the set B defined here? So B is the interval from 1 to 2, closed on this side, open on this side. That's B. And again, on its own, if you're thinking about it as a subset of the real number line, definitely not closed, right? It has one side that's not a closed bracket, so it's not going to be a closed set in the Euclidean sense. However, it is relatively closed in our subspace, and we can use the same logic there. The same logic being, it's the intersection of some closed set, and you can pick any old set, really. I mean, any old set that's like larger than it. But yeah, there's, maybe I'll call it F, because we like to use F for closed. There's our set F, and we know that B is equal to the intersection of F with Y. Right. Imagine intersecting the teal and the purple, you get the red. And so it doesn't matter that it doesn't look like a closed set on its own. It is relatively closed in Y. Cool. Another weird thing, you can always say that your subspace is clopen in itself. So it's both relatively closed in itself and relatively open in itself for, you know, similar reasons. Let's use teal again. I could say it's relatively closed because, hey, look, it's, you know, this set F intersected with Y, and F is definitely a closed interval in the real number line. But it's also an open set in the real number line intersected with Y. So that's always going to work. Your subspace is always clopen, relatively clopen in itself. Let's see some other examples. So let's say we work in R2. This lets us draw prettier pictures. So the open sets in R2 are generated from the open balls, because we're thinking of the Euclidean topology. But basically, my rule of thumb is just going to be anything I draw with dotted lines will be open. Anything I draw with solid lines will be closed. So we'll just use that convention. And let's draw something that's relatively open. And let's fill that in. So let's call that A. And A is actually equal to, I mean, you look at it and you're like, wait, it's closed on this corner, right? I drew a solid line on that corner, so how can it be open? Well, it's not open, it's relatively open in Y, or in S, I meant to say. S is our subset, the square with side length 2, I suppose. And I'm thinking about the square being filled in. I just don't want to draw it filled in. But anyway, imagine the square is filled in. Then A is actually equal to some larger set, right? So some larger open set, maybe I'll use teal, intersected with S. S. And we know this is some set U, then U intersect S is A. So A is relatively open because really, I mean, I like the 2D examples because you can imagine generating all possible open sets really easily. Just like take this set U and slide it around. And then wherever it intersects the square, that's a relatively open set. You know, even if U ends up being entirely in here, so that's U, U is also relatively open in the square, right? It's kind of trivially relatively open. But yeah, you can imagine sliding around, getting a whole bunch of different relatively open subsets. Maybe you do something even wackier and say like, oh, this set B, that's B, is relatively open because it's equal to, I guess I should have put a border on it. It doesn't extend outside the square. And we say it's relatively open because, you know, here's some open set F that when I intersect it with the square, I get B. Okay, so that's what relatively open means. And you can do all sorts of similar stuff with relatively closed sets. Let's get our purple marker back out and just draw some relatively closed things. So I'm giving that a border. That's relatively closed. Similarly, this is relatively closed. Even if I made the border of the yellow square an open set. And maybe I'll do that. Let's actually slide this down. Let's redefine our square. I'll call the square on the right Q. And we'll say Q is sort of the open square. So the largest absolute value that the coordinates have is strictly less than 1. And let's redraw this. So now I have an open square. Again, it's filled in. So imagine it filled in. And even if I do things like this, where it's, you know, it looks open on that corner, it's actually relatively closed. So we'll call that C. And it's closed because I can take some closed set like that. So the red set is closed in R2. Intersecting it with the open square makes it look like it's half open, half closed, but really it's relatively closed because we're not worrying about anything outside of the square. The only thing we care about is inside the square. So this is the square Q. Cool. You can generate as many examples as you want like that. Yeah, and that's it. Thanks for watching.